Welcome to another unit on the simplex algorithm. As exercise, we have simply, by using simplex algorithm, calculate the optimal solution to the following linear problem. Now we have a maximization problem, and in addition to the objective function, we also have three constraints, which I'm just going to list here. So the objective is maximize the function 3x1 plus 2x2 under the constraints 3x1 plus 3x2 smaller or equal to 300, 6x1 plus 3x2 smaller or equal to 480, and finally 3x1 plus 3x2 smaller or equal to 480. Finally, we have our non-negativity constraints that both decision variables need to be positive or zero. Well, we could simply continue with this program, with this problem here, and solve it, but this would not necessarily be the most efficient way to solve this issue, because first off, we can simplify our problem by dividing the inequalities by 3. So this would translate into x1 plus x2 smaller or equal to 100. And here 2x1 plus 1x2 smaller or equal to 160. This one would also be similar to the first one. That's actually, if we take a look, we see that the coefficients of the first and the second constraint are exactly the same. And well, this one as a value is much smaller than that one. So this first constraint is much more restrictive and constraining than this one. So if we have this one, we do not actually need the third one, since it is always dominated by the first one. So we can just leave it and simplify our problem to this version with 2 decision variables and 2 constraints, which look a bit simpler than they did in the outset problem. Well, with this easier and simpler problem, we can continue to the next slide. So here I just copied the problem as is, and then I have to put this into a table to do my calculations. So I construct a table which has one column per decision variable, so one for x1, one for x2, one row for the objective function, and one row for each constraint. Well, since I could reduce the number of constraints by 1, I have one less row which I need for all my calculations. So it saves quite some time to do this. Well, if I then try to get the numbers into the table, I have to consider first that I have a maximization problem, so the coefficients from the objective function need to be multiplied with -1. So instead of 3 and 2, I include here -3 and -2. Then I'm going to insert for x1 and for x2 0 and get as a first value of the objective function 0. Well, so far so good. What about the 2 constraints? Since they're smaller or equal to constraints, I can take the coefficients and the right-hand side values as is. So I can go 1, 2, put them here for x1, 1, 1, put them for x2, and the values from the right-hand side, 100 and 160, and put them here on the right-hand side. So this table is then already prepared. And I also see, since on the right-hand side there's only positive values, my starting solution is feasible. So I can directly start with my normal simplex. For this, I'm going to take a look at the values in the row of the objective function and select a negative value. I select the absolutely speaking largest negative value, which here would be -3, because 3 is larger than 2. So this will give me my pivot column. In the pivot column, I consider only positive values. Well, both qualify. So then I'm going to divide the right-hand value by this value here. So here I get 100 divided by 1 is 100. 160 divided by 2 is 80. So this is the smaller one. 80 is smaller than 100. So the x4 row will be my pivot row. So pivot row, pivot column, making the 2 my pivot element with which I'm going to do my simplex transformation. That's what I'm doing in the next table. First, I'm going to switch pivot column and row variables, so x4, x1. Then for the pivot element, I replace it by 1 divided by the pivot element. Everything else in pivot row, I'm going to divide by the pivot element, so 1 by 2, 160 by 2, giving me 1/2 and 80. Everything else in pivot column, I'm going to divide by minus pivot element, so -2. So I have 1 divided by -2, giving me this, -3 divided by -2, giving me this. For these 4 remaining values, I have to use a rectangle form for recalculation. What do I mean by this? Well, if I want to recalculate the -2, I consider this like one corner of a rectangle and the pivot element as the opposing corner of a rectangle, giving me this rectangle here with the other 2 corners, -3 and 1. Then I'm going to do my calculation by starting original value minus this value times that value divided by pivot element. So in my particular case, -2 minus -3 times 1 divided by 2. Minus minus cancel each other out, give plus. So -2 plus 3/2 plus 1.5. So this -2 reduces to -1/2. This is what I'm going to do for all 4 values. So here I'm going to work with this rectangle. 1 minus 1 times 1 by 2. So 1 minus 1/2. Here I have this rectangle. So 0 minus -3 times 160 divided by 2. Minus minus again give plus. So 0 plus 3 times 160 by 2, which is 240. Finally, for this value here, I have this rectangle. So 100 minus 1 times 160 divided by 2, so 100 minus 80, giving me 20. So far, so good. So I have my new table. Then I'm going to check again the objective function row. And I see that there's still a column with a negative value. So I have to continue with one more simplex transformation. So this will become my new pivot column because this value is negative. Then I have to consider again positive values here. Well, both qualify again. And consider again the quotient of this value divided by this value divided by that. Then I get 40 and 160. So this one delivers the smaller quotient. So this becomes pivot row. Pivot row, pivot column gives me this 0.5 as pivot element. Then I'm going to do all the recalculation I did before again. First, switching these variables. So I have x3 here, x2 here. For the pivot element, I go with 1 divided by pivot element, giving me 2. Everything in pivot row is divided by the pivot element. So -1/2 divided by 1/2 is -1. 20 divided by 1/2 is 40. And everything in pivot column is divided by the negative pivot element. So -1/2 divided by -1/2 gives 1. 1/2 divided by -1/2 gives -1. And well, that's as far as I get with the easy version. Now I have these 4 values to consider. For this, again, I'm going to use this rectangle form. So this value minus this times this by this. So I have minus, 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 3 minuses, 2 cancel each other out. So 1.5 minus 1/2 times 1/2 divided by 1/2. So in other words, 1.5 minus 0.5 gives 1. For this value down here, well, I could calculate this, but since I have this one and they're both positive, I know that I arrived at my optimal solution. So I do not actually have to calculate this value here because I will not need this. What I, however, have to do is this value and that value. So for this value, I have 80 minus 1/2 times 20 divided by 1/2. So 80 minus 20 gives 60. And for this value, I have 240 minus 1/2 times 20 divided by 1/2. Minus minus gives plus. These two cancel each other out, so I have 240 plus 20, giving me here 260. Well, as I said, since these two values, everything in the objective function row is positive, I arrived at my optimal solution. Optimal solution, so how can I read the values? Well, everything up here has a value of 0. That's also why I inserted 0 in the objective function here in the beginning. Everything here has these values. So x1 has a value of 60, x2 a value of 40, and together they give me a value of 260 in the objective function. Well, so far so good. What I can use this value here for is also one other positive effect, because as I see here, the values are always increasing. So this has the effect when I see that I do a simplex step, this value up here always needs to become larger. If it does not become larger, well, in some cases it could remain the same, but if it decreases, I definitely have made a big mistake. Well, in this case, optimal value, these are the values for my optimal solution. And this more or less concludes my tutorial. I hope you enjoyed. I say goodbye and see you next time.